And we're back. Happy Thursday. Today we will switch gears and talk about feature selection. But before we begin, please, this module is based on information. You could say the reading for it is the following publication tutorial on principal component analysis. Please make sure you're reading through that as part of your reading in support of this module. So we talked about the various components of a pattern recognition system, the pipeline, as it were. We began with the sensor apparatus that gives you the basic pattern information. This can be a physical or a logical device. We talked about feature generation, specifically the features for an image. We talked about the intensity surface gradients. We looked at appearance-based features consisting of color and shape. And then we also talked about hog features, which are a trade-off between local and global representation. So now we're going to focus on feature selection. And in looking at feature selection, we take our features from the feature generation component and we try to answer the following question. What features are relevant to the task? So this feature selection inputs the features that are created by feature generation. And now we're going to pick some of them. Now, the way in which you pick some of them can vary between two approaches. It could be a subset selection. So say you have 10 features, and feature selection picks the best 3 features to represent your data out of those 10 features. Or it could be some function over the features coming out of feature generation. And so one of the questions when we ask this, what features are relevant to the task, we need to know a few things. How do you measure relevance? What's the relationship between the different features? Are any features redundant? And we're trying to reduce the dimensionality. If you have a lower dimension, learning is far more feasible. And there are often statistical methods that you run over the generated features when you're performing feature selection. Okay, so when you construct features, we said that features, when we plot all the features in feature space for a data set, these features are in so-called feature space. And if we examine feature space, such as that are on the right-hand side on the screen, we see a two-dimensional feature space representation, and the points are arranged relative to one another. We call that the geometry of the point cloud in feature space. And so if sometimes you don't like the configuration of feature space, the geometry among the points, maybe it's too difficult to find a function that will separate the points from one another, you can rearrange the geometry of the feature space through some transformation that we call a phi function. So this phi function rearranges the geometry of your data set in feature space. And the hope is that if you find the right phi function, you will get a new representation with a geometry that is more amenable to learning. And so this transformation may do or result in a number of different desirable qualities in the resulting new geometry for your feature space. It might give you better separation between points or data items or records or patterns of certain types. It could eliminate noise, or perhaps it will do away with the fact that there's nonlinearity, meaning that you need a highly nonlinear function in your hypothesis set in order to separate the points from one another if you were trying to carve up your feature space into groups. It also could increase the dimensionality. So these functions, this phi function, could be such that you start with 2 features in the original representation, and that results in maybe 20 features through some combination or function over the original features. So you could increase your dimensionality as well. So here's an example of a class of phi functions called a kernel. And this phi function takes in its input that we have here on the left-hand side of the screen, we have a 2-dimensional feature space. And so what you'll notice here is we have 2 categories of points. We have the red points that are more in the middle. And if you look at the axes, we have the origin for the horizontal axis here, and we have the origin for the vertical axis here. So right in the middle of this coordinate system, that's our origin. And if you look at the points, we notice that for the most part, the red points are closer to the origin, and the blue points are further away from the origin in this feature space. Now, there are some outliers here. Here we have a blue red point that's nestled among the blue points, and here we have a blue point that's nestled in with a red point. But there will always be noise in a data set. What we're concerned with is trying to find a function, a hypothesis that most mimics the ground truth assignment of labels, namely the blue and the red that we depict as being one of some number of categories. And so if we wanted to find a function, well, you can imagine a parabola, which is a degree 2 polynomial, would well separate this feature space such that all the blue points are on one side of or part of the feature space and all the red points are in the other. But it's highly more nonlinear, and we said as you get more nonlinear in a function, you need more parameters, and more parameters means you need more data. And so in very short order, we can transform the geometry of this feature space. And in this particular case, we take the x component, which is the first feature, the y component, which is the second feature with respect to the vertical axis, and we're going to square each one. So for some particular point, let's say we have some vector, and that vector has coordinate x, y in the original representation. Well, with our phi function, we take that input and we produce a new data point corresponding to the original x vector. And that new data point, for its first feature, it has x squared. And for its second feature, it takes that y value, the second feature in the original representation, and it squares it. So when you do that, that's polar transformation. And what that does is it takes all the points that are closer to origin and it makes them closer to 0 in x and y, 2 dimensions. And it takes all the points that are further away from the origin, it puts them more up and to the right in a 2-dimensional representation. So if we look at the resulting feature space, well, here are the red points that were closer to origin in the original representation, and here are the blue points that were further away from the origin. And we see the outlier points here, the red, we get here and here, and then there's another red here that is over here, and then the red and blue together. You'll notice the red and blue together are down there. And so when we do this, what happens? We now go from a degree 2 polynomial that can adequately coincide, as it were, with the ground truth target function labelings down to a degree 1 polynomial. So we've reduced the number of parameters we need for the function that will adequately partition this feature space into parts such that all of the points of one type are on one side of the space and all the points of one type are on the other side of the space. And so this idea of a kernel is a type of phi function that has desirable properties, which we'll get into another time. I can briefly mention it, but that's the subject that's covered extensively in machine learning, which is a prerequisite for this course. So here's a motivating example from a project I worked on called Physical Therapist in a Box. And with this system, we have an inertial measurement unit system. These are the orange boxes you see that are mounted on the major limbs. And the motion capture data from these are used to animate a skeleton, but you also track both the velocity, linear velocity, as well as the angular velocity and acceleration for each one of the joints and the limbs. And so with this information, and here's an actual scan or trace rather of this measurement data, you might in this project want to analyze it. And specifically, we took all of this information and we performed a type of outlier detection to see if somebody's walking gait was abnormal outside of what normal walking gait or parameters should be. And so with that, you can imagine there are a lot of different measurements that you might take, and not all of them are necessary for the task that we had in mind. And so here's the framing problem that we're going to use for this. And it deals with multiple measurements, not all of which you need in order to describe the dynamics of the system that are important. And so we're running an experiment, And with this experiment, we want to understand some phenomenon that's going on through measured quantities. That's the whole purpose of instrumentation, i.e., you want to know the dynamics of some system. How does the system state unfold over time? And so this task is often confounded because this data in practice is going to be imperfect. It's often clouded, so there's all sorts of other influences. It's unclear. You don't know which part of the signal corresponds to what part of your dynamics, or it's redundant that some of the pieces of the data, measurement signals, might be saying the same thing, so you don't need all of them. And in fact, if you don't need all of them, by reducing the dimensionality or the rank of the feature space representation, you're also making learning much more feasible and much better in general. So you also have, this is non-unique, and this is not indicative to computer science. It's typical. These problems of being clouded, unclear, and redundant are typical of any kind of empirically driven science. And so the number of measured variables, like we saw with the physical therapist in a box, it can be very unwieldy. And so we want to be able to make this a little bit more manageable, or a lot more manageable, in order to be able to make sound predictions based on our measurements, just those measurements that are necessary for the types of predictions that we are enterprising to make. And so in the example, we have a spring mass damper system. So we have some spring here, and that spring is such that when you displace it, it exerts a force. We have a mass, and we have a damper in this mass. When you displace it, that spring is going to exert some force, and the force is proportional to the displacement through the spring constant. So the force is in the opposite direction in which you pull the spring. So this is our system under consideration. We have a spring mass damper system, and we have our spring. Here's our spring, and we have a mass. And so we're going to take this mass and we're going to move it. Oops. Let me get my pen. So we're going to take this mass and we're going to move it in this direction. We're going to displace it. And the amount of displacement we're going to call x. It's the delta, if you will, for which you displace it. And when you pull this mass, displace it some amount x, spring is governed by the spring constant. And this spring will want to pull it in the opposite direction, proportional to the spring constant. And so this function f of x minus kx is in the opposite direction. So you displace it, and the spring wants to pull it back proportional to the spring constant in the opposite direction in which it was displaced. And so let's assume we have a frictionless contact point for this mass, and you're going to displace it away from equilibrium. So that means in the beginning, the spring is kind of coiled and our system's at rest, and then you displace it away from equilibrium. So then you pull it out, you release the ball, and because it's frictionless, none of that energy stored in the spring as it's pulling back is going to be dissipated. Is none of that energy in the exerted by the force, exerted by the spring, is going to be dissipated, and so that ball is going to move inward, and then it's going to compress the spring until the spring equals the force coming in, and then it's going to push it back out. And so what you're going to get is an oscillation. That ball is going to move in, then back out, and then in, and then out, and then in, and then out. And in fact, the periodicity associated with this oscillation is directly proportional to the amount of energy exerted indirectly through the displacement that you initiated the system with. And so this oscillation in the spring mass damper system is a function of time because it's going to reach one extreme, and then it's going to take a certain amount of time to reach the next extreme, and then it's going to take that same amount of time to reach the first extreme. And so this oscillation, i.e. its dynamics, describes how the state of the spring mass damper system proceeds over time, its dynamics. And so we know that this is in the x direction. It's along one vector, if you will, in a perfect system. And so our dynamics are a function of a single variable, in this case, x, but we don't really know. We can certainly say the displacement and the motion are along x, but in practice, we don't know the axes or the important dimensions for the system. We can only know through experimentation all the things that we can actually measure about the system we've built. Now, this seems fairly obvious, but it's not always so obvious, and we'll talk about that in a little bit more detail. So this is what happens in general. We're very familiar what it means to be in a three-dimensional world. So let's imagine now we have R3, three-dimensional real valued space, and we have our spring mass damper system mounted. And the spring mass damper system, in real terms, let's imagine this is our x-axis, this is our y-axis, and this last one is our z-axis in ground truth R3 coordinate system. And so in real terms, we instrument our system. And let's say we have three cameras. We have camera A down below. We have camera 3 somewhere up above. And we have camera C, A, B, and C. Camera C is off on the right of the screen. And so in our experiment, we're going to use the cameras to measure the system state. And these cameras are going to track the position of the ball over time. And the hope is that we can take the measurements from this camera and recover the dynamics of the system, this oscillation, this movement over time. And so let's assume that the sample rate for the camera is measuring the position of the ball fast enough that you can reconstruct it. Now, certainly, if the spring is oscillating very fast, you have to make sure the cameras are taking pictures at enough high frame rate that you're not concerned about being able to suitably capture the true motion of the spring mass damper system of that mass. And so each camera, you can assume, samples just so quickly, it's not a problem, say 120 times a second. And the field of view of each camera, the image plane, is going to represent a two-dimensional projection of the ball's 3D position. So what does that mean? Okay, well, the ball's position in 3 dimensions are certainly measurable, but we only know in practice what we can ascertain from the sensors, i.e. from the cameras. So we don't really know the true X, Y, and Z axes. Now, I know I just told you they're there. We know what R3 is, but you don't know these X, Y, Z is typically how most real experiments play out. You don't know the true axes governing the motion that you observe. You only observe what's measured by the cameras. So we choose camera axes representing the horizontal and the vertical components in image coordinates for each one of these cameras. For camera A, that's A vector. Camera B, that's B vector. Camera C, a C vector. So we choose camera axes, and each one of these cameras is at some angle with respect to the system. And so you can see here, camera A is at some angle, camera B is at some angle, and camera C is at some angle. And we know at this juncture, due to perspective distortion, that we're going to get a different view of the system's motion as from the perspective of camera A, camera B, and camera C. But the orientation of these cameras, the coordinates describing the field of view and the image coordinates for each camera, they're not necessarily orthogonal. And we can see here that the plane, image plane for camera B, its axes, governing axes, are not orthogonal to camera C's. They're not orthogonal to camera A's. So you have these non-orthogonal axes describing the motion path of the mass from the perspective of each one of these sensors. But these coordinate systems for each one of these image planes from our sensors, they're not orthogonal to one another. So then one of the questions is, how do we reconstruct this X, the true ground truth motion path, i.e. describing the dynamics of that damper? Can we get a simple equation for X? Can we measure the motion along X? Now, certainly, we could have just in real terms taken the measurements along the x-axis, but this is not what happens in the real world. Typically, we don't know what the best measurements should be that reflect our world dynamics or system dynamics. We know because we use this as an example, in this case, the example for the spring mass damper, but in general, we don't know what the real axes of motion. So if I were to ask you, what are the real axes for the dynamics of somebody who's running by from a camera? Well, which way are they moving? Don't know. It depends on where the camera is. And so you have to rely on the data that comes from the camera. So typically in the real world, We don't know which measurements best reflect the world dynamics or the system dynamics for the object of interest. All you know are what you see from the measurements returned by your sensors. So you have imperfect cameras. That's the other confounding factor. All right, these cameras might be a little bit blurred, or maybe these cameras might be shaken. Right, their mounts aren't perfect, and so the camera is shaking a little bit due to vibrations, and you're going to get a wiggly, if you will, or some noise in the motion path, the motion measurements. So you can have imperfect cameras. You might also have a non-idealized spring. And so when you displace the spring, it's not going to go in a straight path. Maybe it's going to pull to the left or pull to the right a little bit. Maybe it doesn't move straight. So you have lots of sources for noise in your system, measurement noise as well as object noise for the dynamics of interest. And that is on top of the fact that you have these cameras that give you this perspective distortion based on their viewpoints of the same scene. So principal component analysis was intended to try to address this. What it provides is a scheme for trying to figure out what are the most meaningful bases, and I'll describe what I mean by meaningful, but what are the most meaningful basis vectors or axes with which you can express the motion or pose the motion so that you can filter out this noise. So how do you recover the direction, if you will, for the most dramatic part of your system dynamics? And so the goal that PCA accomplishes is to filter out the noise, and you also want to reveal structure in your data. And so in our example, the dynamics of the system, ground truth, are along the x-axis. So that means x hat is the basis along which the x-axis occurs. And so let me write in here the x-axis to give you a reminder. So this is the x-axis, and the x-axis is y, and here's the z-axis. The system dynamics, this motion in and outward of the mass, is going to be with respect to the x-axis. Okay, so that's the true basis, x hat, along which our system dynamics play out over time. Okay, so our goal then is threefold: to find the important dynamics, important meaning the particular principal vector, or the unit vector that describes the direction in which the dynamics unfold; to find the redundant dynamics, because if you have descriptors or features that are telling you the same thing, you don't need all of them, and can therefore reduce the dimensionality of your feature space or reduce the rank of the vectors that describe your object in feature space. And you can also find the sources of noise, those confounding factors like those wiggly paths based due to the camera vibrating, or the off-center mass motion based, resulting from the non-idealized spring. So this is our goal. So let's take a look at the PCA approach. We have noise, we have imperfect camera, and we have a non-idealized spring. So it does not move straight. So what are we going to do about this? So at each time instant, we have the following samples. We have the x-coordinate and y-coordinate from the image plane for camera A. We have the x and y coordinate from camera B. We have the x and y coordinate for camera C. And together, all three of those measure the position of the mass from the perspective of each one of these cameras. So we put them all together, and we call that vector x. And x is going to be a sixth vector, two components of which are contributed by camera A, that sensor, two components of which, or positions of which, are contributed by B, and two components of which are contributed by camera C. So an example of how much data you might get: if you're running for 10 minutes at 120 hertz, that's a total of 72,000 of these six vectors, right? So this data can get very big very, very fast. So we're not concerned about the sample rate. That's just not a consideration for this particular example. And so X has some dimensionality. It's m-dimensional. In this case, our dimensionality is 6. So each X is a 6 vector. And this is because you have a certain number, m many measurements. So in this case, m is equal to 6. So X then, each raw measurement that you get from camera A, B, and C at each time instant of these 72,000 vectors over a 10-minute span, is a point in vector space. And this point is a vector. Each X is in six-dimensional real-valued space, right? And so each x is a point in vector space, and as a point in space, this space is spanned by an orthonormal basis. So we have some set of bases, the linear combination of which give you every single point x in R6 that you're going to encounter from this measurement apparatus. And so all measurements x are some linear combination of your basis. Okay. So if we had a two-dimensional basis, right, this would be the orthonormal basis for this two-dimensional representation. And this basis also reflects how we collect data. Now, of course, if we had these M basis vectors, right, that's going to be represented in matrix form as one of these rows. So there's the first basis vector, here's the second basis vector. If I take the dot product between any pairs, it's always 0. They're orthonormal, and the norm of each one is unit. They're all unit vectors. So in matrix form, the basis vectors are a row vector and is an orthonormal vector, right? The recorded data, any of these x vectors you get in 6-space, is just some linear combination of each one of these rows, right? So that's what it means to span this space. This orthonormal basis vectors is a spanning set, or spans the space. Okay, so what is the ask then for PCA? PCA is asking, can we find another basis different from the basis that gives you the data that you are measuring from your instrumentation? Can you find another basis that's a linear combination of the given orthogonal basis that re-expresses your data? Now, when you re-express your data, you want to do it a little bit differently so that the re-expression of your data is better than it was from the original representation and basis that gave you your x vectors. Okay, so the requirement here is linearity. This PCA requires that everything that you do to combine or change the original orthogonal basis in the new form, it has to be a set of linear operations. And so it's a special set of bases, and it requires this linearity assumption and assumes you also have continuity in the data. No huge discontinuous jumps in the or gaps in the data. No holes, no huge nonlinearities, because you can't use PCA. This is a strict requirement of your data. So let's define a few rigorous definitions that we're going to carry forward in our treatment of what PCA is doing. So we have our data set X, and X, we said, is 6 dimensions for the camera example. We're going to take these M measurements. So here's my first measurement, I have my second measurement, and my mth measurement. And each sample in time is going to be organized as a column vector, and we're calling that matrix of column vectors, or a column matrix. We're going to call that big X. And so big X, each of the columns in big X is going to be one such sample over time. So if we had 72,000 samples, we would have 72,000 columns. And if we had 6 measurements, we would have 6 rows. And so each one of these columns in this column matrix X represents one of our measurements in time. And so this has a name. It's called a design, in statistics, a design matrix. A design matrix is nothing more than posing all of your measurements over time as columns, and depending on standards, rows of a matrix, right? So it's the collection of all of your data together. And so the row index is the number of sample measurements you have, the number of measurements, in our case it's 6, and the n index is the time instant. So let's define the result of a linear transformation, and that result of your linear transformation is going to be the transformed version of each one of these data points in the new basis representation. So let Y be related to X, our original design matrix containing our data. It's the new version, Y, is going to be an M related to X by a linear transformation. So we're going to call X, that's our original data. We have Y is the transformed data, and P, that's our linear system describing the transformation on the original data. Okay, so we write that, we have our Y, and Y is also is M by N. M is the number of measurements, and N is the number of samples, right? So the rank hasn't changed, just the values through some new transformation. Okay, so Y is related to X by linear transformation. So this linear system we're calling P, it has M many rows, where each row is responsible for some aspect of combination among each one of these measurements. Okay, so here, if we're going to multiply this out, we'd say P1 times the first data item, P2 times the second, P1 times the third, P1 times the fourth, P1 times the next one, P1 times the next one. PM times the first one, PM times the second one, PM times the third one, and so forth. So Y, which is M by N, is P, which is M by M, times X, which is M by N. So we have M by N is M by M times M by N. Well, if we look at the outer indices, that's the result is M by N. So yeah, that all matches up. So let's call vector Yi the columns of that resulting transformed version, our column matrix, and let's call Xi vector Xi the columns of X, the original data. So Xi so Xi is the original data, one measurement. Yi is its transformed version. Likewise, we're going to call vector Pi the rows of P. So essentially what we have is a linear change of basis. Remember, at the outset, we said that we were going to change the basis and re-express this data such that the transformed version has desirable qualities about it, better than the original representation. So what's happening here? Our linear system P transforms X to its new form Y, and P is going to represent a rotation and a scaling of the feature values, the vectors of system X. The rows of P, P1, P2, P3, up to PM, are going to be the new basis vectors because we have some linear combination, and that linear combination gives you the new version of our X data that we're calling Y. And so the rows of P are new basis vectors that equivalently describe what we had in the beginning as the individual vectors represented in the columns of X. And so if we perform this product, P times X, the individual values of Y, well, the first column of Y is P1 times X1, P2 times X2, P3 times X3, and so forth, up through and including P1 times Xn, P1, P2 times Xn, PM times Xn, and so forth. And this is a typo. I shouldn't have that M here. So each one of the columns of the Y are going to be each one of these columns in this expanded expression. Let's take a closer look at that. So the columns of Y are as follows. Each Y is going to be the result of the dot product between each one of the rows of P, that's a row of P, with one of the data points. So we take the first row of P, dot product with the ith column, ith data point in X. Then we take the second row of P, dot with the ith data point of X. And then we're going to take up to and including the last row of P, we're going to dot product that with the ith column or the ith data point from X. And so essentially what we're doing, each term in Y is a dot product of each row, the jth row of P, with the ith column of X. Okay. And so we can express that in vector form as Pj dot with Xi. And so essentially what we're doing is we're making a projection. That's what dot product does. We're saying take xi and do the dot product of xi dot with p1, with p2, with p3, all the way up to and including with pm. So you're essentially saying take each one of these vectors from my original representation x and perform the dot product with each one of these p vectors, each row of our transforming matrix. And so the yi, the columns of y, is the result of this projection. So what happens when you do a projection? When you do a projection, you're actually re-expressing a vector's value with a set of coordinates or a set of vectors onto which you're projecting. So let's take an example here. So if I have a vector x here, and let's say I have another vector, let's call it y, and let's call this other vector z, okay? And let's not make it hat, let's make them actual vectors. So if I have x and I want to re-express x's coordinates, let me just 5, 7, in terms of these other two vectors, well, I take that vector, I project it along here, and I project it along here. Maybe I project it along here and I get a value of, I don't know, 2.3. I'm just making these numbers up. Maybe I project along here, I get a value of 7. So that means 2.3 times this plus 7 times that is the description, if you will, of the new representation. So I could represent this as being 2.3 in this direction and 7 units in that direction. So that's what it means to do this projection. And so this y is the new value of projecting that you get when you project this x along these two other vectors y and z. And so the yi column is the result or the value that you get when you do this projection. Okay, so we're going to stop there, and we're going to pick back up on Tuesday with the balance of this, describing this PCA approach. And so we're going to do this projection, but we're going to solve for P that has desirable qualities, and we're going to talk about what these desirable qualities are and end with PCA. All right, so we'll end there. Have a great weekend, and I will see you all on Tuesday. We will be having a project that I've released. It might be released this evening on Thursday night, the 10th, or on Monday. Haven't decided yet. So with that, please stay healthy, stay safe, and I will see you all on Tuesday.